Hello and welcome back. In the previous few videos, we've discussed these advancements which occurred at the early part of the 20th century to try to explain a lot of very strange phenomenons in terms of these very classical ideas like particles and waves. And just to kind of recap what we've talked about so far. So in the very early part of the 20th century, in 1900, Max Planck solved the black body problem. And the way that he solved this was by assuming that a black body only absorbs and emits light in packets which carry an energy which is given by this formula right here. And in 1905, Albert Einstein finally came up with an explanation behind Philip Leonard's experiments involving the photoelectric effect. And basically what Einstein assumed was that the electrons on a metal plate only absorb light in packets that carry the same amount of energy. So basically, Einstein said that the energy that is absorbed or emitted by light is really a property of the light, and it's not just a property of the black body. Many years later, in 1923, Compton observed that light can actually collide with an electron in the same way that two particles collide. And when this happens, you have conservation of energy and conservation of momentum. And when we talked about this, we also mentioned that the momentum of a photon is given by this formula here, although this formula was predicted earlier by Einstein from the theory of relativity. In 1925, this is when the Davison and Germer experiment was performed. This is the experiment we talked about in the last video. It's a very important experiment because this demonstrated that even particles like electrons can exhibit these wave-like properties. So you could actually see an interference pattern formed by these electrons. And we can describe these electrons in terms of these so-called de Broglie waves, which have a de Broglie wavelength and de Broglie frequency, which are found using these formulas already on the screen. And finally, in 1926, Erwin Schrödinger was able to create a underlying theory, an equation, which actually described all of these semi-classical ideas which we've talked about so far. And this is called quantum mechanics. And really, this development by Erwin Schrödinger really marks this dividing line between what we would call semi-classical physics and what we call modern physics. And basically, what Schrödinger was able to show was that all particles, so photons, electrons, protons, neutrons, everything is made up of these things called wave functions. So an electron actually is a wave function. And one really important thing to understand about these wave functions is that these wave functions are neither particles or waves. They're not particles because they don't have a position like a particle, and they're not waves because they don't satisfy the wave equation. Instead, these wave functions are described by something called Schrödinger's equation, which I have written down here. And for comparison, a wave is described by the wave equation, which looks a little bit something like this. We say the second derivative of the wave with respect to time is equal to minus the speed of the wave times the second derivative of the wave with respect to its position. And so we can just see that these two equations are simply not the same thing. So at this point you might be wondering, well, why was there so much confusion about these particles acting like waves? And there's really two major reasons for this. The first is that it turns out that the solution to Schrödinger's equation, whenever the potential energy is constant, so this V right here, this represents the potential energy of the particle. So if this V is held constant, then the solution to Schrödinger's equation is the same as the solution to the wave equation. It's just these moving sinusoidal waves. The second major reason is that Schrödinger's equation is a linear equation, and this means that the superposition principle also holds for Schrödinger's equation. And well, what exactly does that mean? I just mentioned that Schrödinger's equation is a linear equation. Well, let me just go ahead and open up a little blank screen here. So we say that something is linear, an operation is linear, if it satisfies the following properties. So if f of x plus y is equal to f of x plus f of y, and if f of ax is equal to a f of x. And if we look at Schrödinger's equation, there are really only two operations which occur. We're either taking the derivative of the wave function or we're multiplying the wave function by something. And both of these operations are linear. So, for example, if you've taken calculus, you know that the derivative of f of x plus g of x is just going to be equal to the derivative of f with respect to x plus the derivative of g with respect to x. So it satisfies this first condition. Secondly, if I take the derivative with respect to x of a constant times f of x, that's just going to be equal to a times the derivative of f of x. So we can see that the derivative is a linear operation, and also multiplication is pretty obviously a linear operation. So for example, if I take capital A and I multiply it by f of x plus g of x, then by distribution we can see that this is just going to be a times f of x plus a times g of x. Likewise, if I take a and I multiply it by a f of x, this is just going to be equal to a times a f of x. So we can see that multiplication and differentiation are both linear operations. Now it's worth pointing out that there are some operations which aren't linear. So for example, squaring something is an example of something that's non-linear. So for example, x plus y quantity squared, that's not going to be equal to x squared plus y squared. So squaring something is not a linear operation. And the reason that linearity is so important is that because of these two properties, if I have one solution to Schrodinger's equation, and then I have a second solution to Schrodinger's equation, so I have two functions, both of which satisfy Schrodinger's equation, if I add those two things together, I will still have something that satisfies Schrodinger's equation. And that's really the basic underlying mathematical principle behind the superposition principle. So that's really what's going on when we're using the superposition principle for waves or anything else. So the superposition principle is really this general thing that applies to any equation which is linear. So because Schrodinger's equation is a linear equation, it has superposition, and because the solution to Schrodinger's equation, when the potential energy is held constant, is the same as the solution to the wave equation, Schrodinger's equation really looks like the wave equation whenever the particle is moving through free space. And when an electron is not held in a constant potential, these wave functions can look very different than regular waves. So for example, if I have an electron which is held in some kind of harmonic potential, so for example, if I had some kind of magical spring attached to this electron that's always pulling that electron back to its equilibrium, then the wave function that would describe this electron looks something like this distribution that I have shown here on the screen. And this is a Gaussian distribution. So if you've ever taken a class in statistics or probability, you've probably heard about the normal distribution. That's the same type of distribution that describes the wave function. It's held in a harmonic potential. And one very important thing to notice about this is that this electron doesn't just exist at any one point in space. This electron is described by this wave function, which exists over a region of space. So this electron really exists over an entire region of space. And we describe how spread out this distribution is with something called the uncertainty in the particle's position. And you may wonder, well, why do we call it an uncertainty? I mean, shouldn't we call this the spread in the particle's position? Calling it the uncertainty in the particle's position almost seems kind of misleading, because it's not really what I'm saying. I'm saying this is how spread out this distribution is. So to understand why we call this the uncertainty, suppose for a moment that I try to measure the position of an electron, and let's say this electron is described by this very broad wave function that I have shown here. And let's say I just shine a whole bunch of light on this electron, and then I observe how those photons scatter off of the electron, and I try to use that to calculate the initial position of the electron. Well, whenever I do this, it'll always look like that electron existed at a single point in space. I'll never see an electron which looks like this kind of distribution over here. It'll always look like the electron was at a single point in space. And the reason is that when this electron interacts with, for example, the light that I'm shining on the electron, that interaction will cause this wave distribution, this wave function, to evolve forward in time into something that looks like this. And this phenomenon, where a wave function that is very broad evolves forward in time into a very narrow wave distribution when you try to measure the particle's position, is called a quantum mechanical wave collapse. And we would call this type of distribution over here on the right a very particle-like distribution, because even though this wave function exists over some region of space, because the region that the wave function exists over is very narrow, it's almost like the wave function has a position. So it's almost like it exists at a single point in space, just like a particle would. And one thing that I should mention about quantum mechanical wave collapse is that this is still a very active area of research, and it's very closely related to something called decoherence. And what decoherence is that if you have some kind of wave function, if that wave function is interacting at all with its environment, which naturally is going to be a very complicated thing that involves many, many different particles, then that wave function that you have is always going to evolve forward in time towards very specific types of states. And that's exactly what happened here with this electron. When we shine a whole bunch of light on the electron to measure its position, that electron interacts very strongly with its environment, namely the light that we're shining on the electron, and that causes the wave function to evolve forward in time into these very specific types of states. In addition to having an uncertainty in their position, wave functions also have an uncertainty in their momentum. Now, what exactly does that mean for a wave function to have an uncertainty in its momentum? Well, if we consider some kind of classical object, say for example a ball which is rolling along, well, the momentum of a ball is equal to its mass times its velocity. So an uncertainty in the momentum of the ball really means that we have an uncertainty in the ball's velocity. So say, for example, I measure the speed that this ball is traveling at as being equal to v plus or minus delta v. So this delta v is describing my uncertainty in the speed that the ball is traveling at. Now, if I try to calculate the position of this ball at some later time, delta t, then this uncertainty in its velocity, this delta v, will manifest itself as an uncertainty in the position of the particle after some time delta t. So for example, if the particle is traveling on the faster end of my estimate, so say for example it's moving at a speed of v plus delta v, then the particle will move further, or the ball will move further. If the ball is traveling on the slower end, say of v minus delta v, then the ball will move a shorter distance. So what we see is that the uncertainty in the momentum manifests itself as a growing uncertainty in the position of the particle. So the uncertainty in the momentum describes how quickly my uncertainty in the position will increase. And that's exactly what the uncertainty in the momentum of a wave function describes. So the uncertainty in the momentum of a wave function describes how quickly the uncertainty in the position of the wave function will increase. So in other words, it's describing how quickly this distribution will spread out as it moves along. And it turns out that the uncertainty in the position of a wave function and the uncertainty of the momentum of the wave function are limited by something called the Heisenberg uncertainty principle. And what the Heisenberg uncertainty principle says is that the uncertainty in the position of a wave function times the uncertainty in the momentum of the wave function must be greater than or equal to Planck's constant divided by 4 pi. And one thing that I really should emphasize about the Heisenberg uncertainty principle is that the uncertainty principle does not simply limit our ability to measure the position and momentum of some particle. It really says a whole lot more than that. So, for example, if I had an electron which was in a harmonic potential, so it's acting like a particle attached to a spring, and I know with 100% certainty that that particle is in its lowest energy state that is allowed by Schrodinger's equation, then I know with 100% certainty what that particle's wave function is. So that wave function, I can sit down, I can solve Schrodinger's equation, and I can show that that wave function is a Gaussian. So I know with 100% certainty what that particle's wave function is. And then if I suddenly turn off the potential so that wave function is now allowed to evolve freely in time, I can solve Schrodinger's equation and again calculate exactly what that wave function will look like at some time later. So I'll say that that wave function is going to look a little bit like this. These distributions moving in opposite directions. Now what the uncertainty in the position is describing is it describes how spread out that wave function is. And the uncertainty in the momentum describes how quickly that spread will increase if I suddenly turn off the potential and I just let that wave function evolve freely in time. So what the Heisenberg uncertainty principle is really limiting is not just your ability to measure the position and momentum of a particle. So for example here, I knew exactly what the wave function was, but there was still an uncertainty in its position. And here I knew exactly what the wave function was, but there's still an uncertainty in its momentum. What the Heisenberg uncertainty principle is really saying is that there is a limitation on the types of solutions to the Schrödinger equation. In other words, there are no solutions to the Schrödinger's equation which have an uncertainty in their position and an uncertainty in their momentum that are less than Planck's constant divided by 4 pi. And you can actually mathematically show that there are no solutions which violate the Schrödinger equation. This is something that you can mathematically derive from Schrödinger's equation. So at this point we may wonder, well, where exactly does this uncertainty principle come from? How do you show this uncertainty principle? Because I just said that we can derive it. Recall that any distribution can be described in terms of a sum of sine and cosine terms with different wavelengths. So for example, if I want to describe this wave function which is traveling towards the right, I can do that by adding together a whole bunch of sine and cosine terms with different wavelengths. So if I keep adding together more and more sine and cosine terms, this will begin to look more and more like the wave you saw on the previous slide. And the reason that this is really important is that in order to describe any type of wave function which is confined in space, so the uncertainty in its position is not infinite, so it exists over some region of space, then I'm going to have to add together a whole bunch of sine and cosine terms, and each of these sine and cosine terms will have different wavelengths. And remember that the momentum of a de Broglie wave is related to the wavelength. So if I have to add together a whole bunch of waves that have different wavelengths, then I'm going to be adding together a whole bunch of waves that have different momentums. So whenever I have a wave function that is confined in space, I will necessarily have an uncertainty in the momentum. And that's really where the Heisenberg uncertainty principle comes from. It comes from this real basic principle regarding Fourier series, and that's where you add together these sines and cosines to describe another type of function. Now let's take a look at a couple of examples. So this first example says the diameter of a hydrogen atom is 10 to the minus 10 meters. What is the minimum uncertainty in the momentum of an electron inside a hydrogen atom if the uncertainty in the position is equal to the diameter of the atom? So we're told that the uncertainty in the position is equal to 10 to the minus 10 meters, and we're asked to find the uncertainty in the momentum of the electron, or the minimum uncertainty in the momentum of the electron. Well, according to the Heisenberg uncertainty principle, the uncertainty in the position times the uncertainty in the momentum must be greater than or equal to Planck's constant divided by 4 pi. So the uncertainty in the momentum must be greater than or equal to Planck's constant divided by 4 pi times the uncertainty in the position. So Planck's constant is 6.626 times 10 to the minus 34 joules seconds. And then we have 4 pi, and the uncertainty in the position was 10 to the minus 10 meters. So if we plug these numbers into a calculator, we can see that the uncertainty in the momentum must be greater than 5.27 times 10 to the minus 25 kilograms meters per second. Let's take a look at another example. So the second example says, what is the uncertainty in the position of a hydrogen atom at 300 Kelvin, assuming that the uncertainty in the momentum is equal to the mass of the hydrogen atom times the RMS speed. So here is the mass of hydrogen atom, and remember, the way that we calculate the RMS speed for a gas is that we use this equipartition theorem, which says that the kinetic energy, or the average kinetic energy, is going to be equal to 3/2 kT. So that's the average kinetic energy of an atom inside a gas. And the kinetic energy is also equal to 1/2 m times the RMS velocity squared. So we're going to need to calculate this RMS velocity to calculate the uncertainty and the momentum, because we were told to assume that the uncertainty and the momentum was equal to the mass of the hydrogen atom times this RMS velocity. So one way I could solve this, I think a kind of an easy trick to solving this, is if I just multiply both sides by the mass of the particle. Then on the left side, I'm going to have 3 halves mkt, and on the right side I have 1/2 mv quantity squared. So we can cancel out the 1/2, and if we think about this, mv is momentum, so I'm saying the momentum squared is equal to 3 mkt. So my momentum is equal to the square root of 3 mkt. So this is the uncertainty in my momentum by my assumption that the uncertainty in momentum is equal to m times the RMS velocity. So now all I have to do is plug this into the Heisenberg uncertainty principle to find my uncertainty in the position. So we have the uncertainty in the position times the uncertainty in the momentum must be greater than or equal to Planck's constant divided by 4 pi. So the uncertainty in the position is going to be equal to Planck's constant, greater than or equal to Planck's constant divided by 4 pi times my uncertainty in the momentum. And the uncertainty in my momentum, if I plug these numbers into a calculator, I'll see that this is equal to 4.56 times 10 to the minus 24 kilogram meters per second. And if I plug that into this equation over here, I'll see that the uncertainty in the position of the atom is equal to 1.15 times 10 to the minus 11 meters. And just to put this into perspective, the diameter of a hydrogen atom is about 1 angstrom, which is about a 1/2 of an angstrom. So that's about 5 times 10 to the minus 11 meters. So we can already see that the uncertainty in the position of the atom is actually less than the size of the atom. So this is a very, very insignificant uncertainty in the position of the particle. And there's one last thing that I'd like to talk about before we move on and begin discussing atoms, and that's Schrödinger's cat. And the reason that I like to bring up Schrödinger's cat is this is one of those things that's kind of entered into popular culture, and I think a lot of people have heard about Schrödinger's cat, but it's also one of those things where there's a lot of misconceptions about what Schrödinger's cat actually is. So in the early part of the 30s, people were studying Schrödinger's equation, and they were seeing all sorts of really strange things. So, for example, we've already talked about this idea that if you have an electron, which is in a harmonic trap, then you get this kind of quantum mechanical wave function that looks like this. It's this Gaussian wave function. And people looked at that and they said, well, that's kind of strange. It kind of looks like this electron's in a whole bunch of different places at the same time. So it's like the electron's in this quantum mechanical superposition of many different places all at the same time. Another example of this is that if you have an unstable nucleus, so you've got a nucleus that, say, has maybe too many neutrons in it or something like that, then what will happen is that over time the nuclei will decay. So the nucleus might emit something like an alpha particle, which is 2 protons and 2 neutrons. And according to Schrödinger's equation, if you have an unstable nucleus, as time goes on, the nucleus will evolve into a quantum mechanical superposition of both decayed and undecayed states. So that's what Schrödinger's equation says will happen. And by the middle of the 1930s, people were really starting to take this idea of quantum mechanical superpositions to sort of absurd extremes. So, for example, Albert Einstein said, well, so if you had a barrel that had this really unstable gunpowder in it, then as time goes on, the barrel will evolve into exploded and unexploded states. And Schrödinger said, well, this whole idea of quantum mechanical superpositions is just completely crazy. And actually, I don't know enough about the history of physics. I'm not completely sure whether Schrödinger thought that quantum mechanical superpositions in general were crazy or just the quantum mechanical superpositions of macroscopic states were crazy. But to really just explain how crazy this idea of these quantum mechanical superpositions was, he came up with this experiment And the experiment's never been done before, so you don't have to worry about harming any cats. But the basic idea is that he said, well, let's suppose you had this box, and it's a completely sealed box, so you can't see inside it, and inside the box you have a cat. And inside the box you also have some kind of radioactive material. And suppose that there is a 50% chance that one of the atoms inside here will decay, emitting an alpha particle in the next hour. And there's a 50% chance that none of the atoms inside this thing will emit any alpha particles. And furthermore, let's suppose that we have some kind of sensor, a Geiger counter, which will detect whether or not any of the atoms inside this box have decayed. And then attached to the Geiger counter is a device which will release poison, so that if an atom decays, poison is released, killing the cat. And if none of the atoms inside this box decay, then the poison is not released and the cat is spared. And what Schrödinger said was, well, okay, according to the Schrödinger equation, the nuclei of the atoms inside here are in these quantum mechanical superpositions of decayed and undecayed states, which would mean that the Geiger counter is in a quantum mechanical superposition of states where it detected a decay and a state where it hasn't detected a decay, which furthermore means that the poison is in a quantum mechanical superposition of states where it's released the poison and it hasn't released the poison, which would finally mean that the cat must be in a quantum mechanical superposition of both dead and alive states. And Schrödinger said, well, this is just completely ridiculous. So this idea of these, macroscopic quantum mechanical superpositions, it's just completely ridiculous. And I should point out that pretty much all physicists agreed with Schrödinger. They said, well, yeah, this is obviously completely ridiculous. So I can't think of a single physicist who actually thought that Schrödinger's a cat was in a superposition of dead and alive states. So how do we actually explain what's going on? Why is the cat not in a superposition of dead and alive states? And the reason is because of quantum mechanical wave collapse. It's because of decoherence. So remember, if I have an electron, which is in, say, some kind of wave distribution that looks like this, if that electron interacts very strongly with its environment, then that wave function will collapse into a state that's very compressed, like this. And the same thing is true for the nuclei of the atoms inside here. So because these atoms are very, very strongly coupled to their environment, right? They're very strongly coupled to this Geiger counter and this device and this cat. So because all of these things are very closely linked together, these nuclei inside here are very strongly coupled to their environment, which means that they are perpetually in a collapsed state, which means that these nuclei can't be really in a superposition of decayed or undecayed states. They're going to instantly collapse into either one or the other. So you never have a superposition of decayed and undecayed states in here, which means you never have a superposition of dead and alive cats. And it's all comes back to this idea of decoherence. And we can show that basically if you have a very large system with a very large number of particles, it will decohere very, very quickly. And if you have just a few particles, then the decoherence times are very long. So for example, if I have an electron which is in a state like this, so it's described by a wave function that looks like this, and that's way out somewhere in space where there's nothing around it, then that electron will stay in this quantum mechanical state for pretty much forever. But if it's in a place where the electron is strongly interacting with its environment, then the electron will very quickly start to collapse. And then as time goes on, this state will evolve forward in time into maybe another spread out state, but again, it'll almost instantly be collapsing all the time. And that's exactly what's happening here with Schrödinger's cat. Because the radioactive material is always in a collapsed state, the cat is never in a quantum mechanical superposition of dead and alive states. So that's really all I wanted to say about Schrödinger's cat. And the next thing we'll talk about are atoms and what's actually going on inside the atoms with these electrons.